Okay, so welcome everybody. So we have a real treat today. So we have a very distinguished guest speaker, Cleve Moeller, who's been a leading figure in scientific computing for over 50 years. So he's one of the co-authors of IcePack and LinPack, which are the libraries on which almost all the linear algebra computations we do are based. And he also invented Matlab, which I and probably many of you use or will use in the future. So, well, yeah, I feel really great that he's giving a talk in our course. So please, Cleve.
Hello, everybody. Nice to be talking to Berkeley. I'm going to tell you quickly about two of my very favorite subjects, Matlab and the singular value decomposition. And this business about saving the universe will become apparent in a minute. I do the SIAM is a Society for Industrial and Applied Mathematics, and I'm a visiting lecturer in SIAM, so I give talks like this to SIAM student chapters. So you're getting the SIAM visiting lecture tonight. You're all familiar with your computing environment here. All of our computing environment involves things like laptops and cell phones and Google and MATLAB. And I want to go back even more than 50 years, back to a time like this. This is where I first got involved in computing, with paper tape and punch cards and computers that filled a whole room. Both of these were personal computers. Only one person could use them at a time. When I was a grad student at a school across the bay from Berkeley that you may have heard of, we had the singular value decomposition was just a theoretical concept. Forsyth and I wrote this book, and the SVD is mentioned just as a way of talking about the norm of a matrix. One day at a seminar, Forsyth said, "Why doesn't somebody figure out how to compute the damn thing?" And Gene Golub did. Golub was a new professor at Stanford, and together with Velmo Khan from Berkeley, invented the algorithm for computing the singular value decomposition that we still use today. Golub is famous for many things, but he was perhaps most pleased with this SVD, as his California license plate showed. By the 1970s, I was a professor at the University of New Mexico, and I spent a day a week at Los Alamos National Laboratory working on subroutine libraries for the supercomputers. And while at Los Alamos, I made a film, actual 16 millimeter celluloid film. This is for two reasons. One was to promote the singular value decomposition, which was then only a few years old. And the other is to experiment with the Los Alamos graphics library. You're going to see some pretty crude graphics in a minute right now. Even back then, it was even fancy stuff to put Greek letters on the screen. So here's a part of the film I made at Los Alamos in 1976. I'm going to use this as a way of really telling you about the singular value decomposition, how it works. Oh, are you getting the sound on that?
No.
No sound.
Professor, I think you're muted.
Oh, sorry,
No,
we're not getting the sound.
I have to share video. I have to share audio.
Yeah, so you have to unshare and then reshare with share audio, I think. Yeah.
Sorry about that. So unshare. Where is, so share screen, share sound. There's the key right down there. Then I want to go back and I need it. There,
So
need
I
to
think we
put
still
that
don't. Yeah,
up.
there you go. Uh-huh.
And I want to go back to the start of this. You got sound now?
The computer is used to simplify the matrix so that most of the entries will be zeros.
Are you hearing this?
One method is known as the singular
Yeah,
value decomposition. The original matrix is represented as the product of three matrices. In the second of these matrices, the only non-zero elements lie on the diagonal. The other two matrices must preserve the properties of the original matrix. So they are orthogonal matrices. Each is the product of elementary matrices, which affect only two rows or columns. Scientists at Los Alamos Scientific Laboratory have been studying methods for the accurate and efficient calculation of the singular value decomposition and of describing to computer users how the computation is carried out. In this three-dimensional representation of a small matrix, each pyramid depicts the magnitude of a single matrix element. The diagonal of the matrix runs from the upper left to the lower right. Orthogonal transformations will be used to introduce zeros into the matrix. The initial transformations put zeros into the first row and then the first column. Each transformation affects two other columns or rows shown here in blue. Later transformations introduce zeros into later rows and columns while preserving the zeros already obtained. The second stage of the calculation is a repetitive or iterative process which reduces the size of the remaining off-diagonal elements, but does not zero them in a single step. The calculations now being shown are primarily intended to reduce the size of the off-diagonal element at the lower right-hand corner. Once an off-diagonal element has reached a negligible magnitude, it is set to zero. The computation of the corresponding diagonal element is then complete, and the resulting singular value is shown in blue. The final diagonal matrix, together with the two transforming matrices which produced it, then provide the basis for a complete analysis of the original matrix and the system which it models.
Okay, that was the entire film is 6 minutes long, and if you Google S3D, Molar S3D on the, you get the YouTube link to the entire film. I'm not monitoring the chat. If Neil, if you see what's going on with the chat, keep track of that. Let me know.
Yeah,
if there's
people
something.
love the soundtrack. I mean, I thought it was great too, but no questions.
All right. Well, now watch this. Shortly after I made that film, producers from Paramount Movies came to Los Alamos looking for video to use on in the displays on the Enterprise, on the bridge of the Enterprise. They're making the first Star Trek movie, Star Trek: The Motion Picture. A mysterious force called V'ger is threatening the universe, and our intrepid band during the Star Trek is going to save the universe from V'ger. Now, look over Spock's shoulder here. That's the SVD going on
A
the
maximum phase
screen
strike
behind
directly at the
Spock.
beam might weaken it just enough for us to break free.
Break free to where, Commander? Any show of resistance would be futile, Captain.
We don't know that, Mr. Spock. Why are you opposed to trying? Why bring us inside? Not to destroy us, They could have done that outside.
They still can.
Curiosity, Mr. Decker. Insatiable curiosity.
I had to play that until we saw Spock's eyebrows there. Okay, so the SVD is going on the screen behind over Spock's shoulder throughout the entire movie. And if you zoom in on it, just taking it out of the film, it's in poor resolution. But you go back to the original film, and this was what was being used in the movie. Okay, so SVD is going to save the universe. At the same time, I was working on LinPack and IcePack, which were Fortran subroutine libraries for doing matrix computation. Here's the authors of LinPack at the time we were working on it, and the same authors 35 years later. Dungera this is Jack Dungera, me, Pete Stewart, and Jim Bunch. Dungera's lost the most hair, but I have the neatest shirt. I was teaching this course, the course you are taking now, right now. I was teaching that course back then, and I wanted to have my students have access to LinPack and IcePack without writing Fortran subroutines. So I wrote the first version of Matlab in Fortran in the late 1970s. Here's the screen, the greeting screen, the splash screen of the first Matlab. This is all the functions there were. It isn't a programming language. There are no M files. There's no differential equations, no FFT, just this simple matrix calculator. But one of the things within it was the SVD, which was then new at the time. So here is some output from that original Matlab, and I'm going to use this matrix as my sample. This is a magic square, an 8x8 magic square. I've been interested in magic squares since I was in junior high school. What is a magic square? Well, let's let E be the vector of all ones. And if I do a matrix vector product, A times E, this is what you type in MATLAB. MATLAB types back this, and that is the sum of all the rows in A. All the rows in A add up to 260. All the columns add up to 260. The diagonal adds up to 260. To get the other diagonal, you have to flip the matrix. That adds up to 260. Why is it 260? Well, the matrix is made up of the numbers from 1 to 64. If you take that sum and divide by 8, you get 260. So the magic sum of an 8x8 magic square has to be 260. If I want to solve a system of linear equations where the right-hand side is all 260s, I know one solution. The solution is that x equals all ones. Here's the MATLAB backslash character. This has become the iconic operation in modern MATLAB. But here it complains because the matrix is singular. Why is it singular? Well, I compute the SVD of that magic square. Here's the singular values of that magic square. The biggest one's 260. Why is it 260? Well, if I was assigning homework in this course, that would be your homework. Prove that the largest magic square, prove that the largest singular value of a magic square is the magic sum. Now it's easy to prove that the magic sum is a singular value. Proving it's the largest is actually a little bit subtle. And this particular magic square has 2 other non-zero singular values, and then 5 of the singular values are 0. So the fact that this one of the singular values is 0 is what's saying this matrix is singular, but the fact that there's have 5 of them was kind of a surprise. I can do the full singular value decomposition, in which I compute not only the singular values, but also the singular vectors. Again, it gives me 8 by 8 matrices, but I take just the first 3 columns. So U is the first 3 singular vectors, right singular vectors. V is the first 3 left singular vectors. And if I form O, then I just take the non-zero part of the diagonal, which is only 3 by 3. And if I do U times S times V prime, V transpose, the prime here stands for transpose, I get back the original matrix. So I'm able to reconstruct the 8 by 8 matrix out of just this 3 by 3 matrix. And Nikhil, there's something that's your heart that you love, that's being able to have low rank approximations to matrices. Here it's not only an approximation, but you get back the exact matrix. Now back to solving the system of equations. If I want to solve AX equals B, here it is written out in terms of the singular values. Here's the backslash again, but this is only involving a diagonal matrix now. And now I get the vector of all ones that I was expecting. Okay, this was kind of a joke back then. I didn't have any graphics in Matlab. Here's a plot command that can just use the printer characters to do a plot. And here's the singular values. Here's 3 non-zero singular values, and the rest of them are 0. So this plotting, crude as it is typical of what we want to see when we do low rank approximations to matrices based on the singular values. Okay, that was the original Matlab. That's about all it could do. I visited Stanford in a sabbatical in 1978, and 1979, I used that Matlab. The computer science students, lab students weren't impressed. The engineering students loved it. I'm going to have to speed up now. The engineering students, one of them took it to this guy, Jack Little. Little didn't take my class, but a friend of his did. And Little started using Matlab in his work on control theory. He came to me in 1983 and said he wanted to make a commercial version of Matlab. So he went into the hills behind Stanford, re-implemented all of Matlab. Oh, he bought this computer down at Sears, went and used Matlab and rewrote it in C, introduced M files, introduced toolboxes, and the MathWorks Matlab made its debut in 1984. Little was the only employee of the company in 1984. The population of this is a log plot of the size of MathWorks over the last 35 years. The company doubled in size every year for the first 7 years. Now it increases, it doubles in about every 5 years. Here's the company when there was only 8 people in it. I didn't work for the company for the first 5 years, but by 1989, I came to work for my own company. Here I am over on this side. Here's Little over here. By 2005, we had companies, branches all over the world. Here's the company picture in 2005. And now the company's too big to get us all together at once. Here's 3,000 people in this auditorium a couple of years ago when we celebrated our anniversary. So here's a few facts about MATLAB, about MathWorks, the company. We have over 5,600 employees now, almost half of them outside, a third of them outside the US. The company is privately held. It's been profitable every year. I was amazed when I saw this statistic that 500,000 people visit the MathWorks website every day. Here's the company headquarters in Natick, a suburb of Boston. And here's a second campus we opened just last year alongside this lake in Natick. Matlab has gone way beyond being a matrix laboratory. It's used in all kinds of, lots and lots of industries. Electric cars, image processing, hearing aids, control of mathematical biology. These are Matlab's real power and commercial success comes from its toolboxes, which are Matlab, pieces of Matlab code, libraries of Matlab code in specific vertical application areas. You may not have seen this part of Matlab, where it's used in all these businesses, all these industries, fields. There's a companion product called Simulink. That's a whole nother world. Here's Simulink for signal processing, robotics. Here's automated driving and lane detection. Okay, back to the SVD. Let's see, I'm gonna aim here at, you
can go a little over if you need to, that's fine.
Yeah, I will. There's something I definitely want to show you here. There's a related business called principal component analysis. It involves taking your data, centering your data and getting orthogonal components to describe your data. Principal component analysis is usually defined in, let's not get through it. Let's go back. Let's get that. I want to show you this example. This is the human gait. This Nicholas Troji was a professor in Germany. He's now a professor in Canada. He wants to understand how we as human beings can watch other human beings walk and learn things about them from the way they walk. We can see how old they are, maybe. We can see their gender, see what their mood is. How do we do that? How do we get that from the human gait? He makes videos of people walking on a treadmill and captures their motion. He takes 15 markers on the body, looks at them in 3 dimensions. So he has 45 functions of time, 45 time series. He takes a few thousand frames for one subject. And so his raw data for one subject is a matrix with 45 rows and a couple of thousand columns. Remember the 45, that's an important number. Here's what the data looks like. Here's some of those 45 functions. They're periodic because they're almost periodic, sort of periodic because our walking is periodic. But Troji wants to simplify the presentation, the study of it with a model, a reduced order model. So here's Troji's model. It's a 5-term trigonometric series, Fourier series. there's one nonlinear parameter, omega, which is determined, which is computed using Fourier analysis. But the coefficients here, V1 through V5, are the vectors. They're the vectors out of the SVD. He takes the matrix with 45 with thousands of columns and reduces it to a matrix with only 5 columns. So this is actually a linear space. It's a time varying linear space, but it as a linear space, it has dimension 5 by 45. 225 is the dimension of this space, because you can have any coefficients here.
Oh, we actually can't hear you now, like from a couple of seconds ago. Maybe you can try to mute, unmute. Oh, his screen froze. Okay. Maybe we'll just wait a little bit. Oh, well, I guess we can just wait a little bit for Cleve to come back. Yeah, let's just wait a little bit.
How's your day going, Professor?
Oh, good, good. Yeah, really good. Well, we're thinking of buying a house, so it's pretty, it's pretty hectic. Yeah. How's everybody else? Huh?
Did you got engaged over spring break, or did you get married over
I got
spring break?
engaged over spring break, yeah. So, yeah, I guess.
When's the wedding going to be?
Oh, we're not sure because of COVID, but yeah.
Do we get a Zoom link that we can?
Oh, if it's televised, yeah, sure. I mean, yeah.
Can we get an invite if it's in person?
If it's big enough, yeah, sure. I mean, unfortunately, I think it's going to have to be really tiny, but we'll see.
Do we have to solve a problem before we can gain admission?
Do you want to solve a problem before getting admission? So let me email Cleve and to see if he's
Max, how are you doing today?
Doing good, pretty good, Isaac. Just pretty relaxed Thursday.
Nice.
How have your classes been?
It's been great, you know. It's that last lecture of the day, feeling good.
Yeah.
They just homework, you know how it is.
You learn a lot today?
Oh yes, I had physics today. It was amazing. Yeah, we talked about capacitors.
Oh, you talked about capacitors. It's kind of related to that spring stuff I was talking about.
How far? Well, what do you want to do? It's up to you guys. You got more things to do with your class, don't you?
Yeah, but this is really interesting. So maybe we continue, and then I'll figure a way to do the other stuff in time.
How far did we get?
We got to the gate analysis where you had this 45 by 5 matrix.
Yeah. So share screen. You need to enable me to
Oh,
share.
sorry. Yeah. I need to make you co-host again. Yeah, okay. You're a co-host. Yeah, and now you can share.
I don't need to share sound anymore. Let's see, well, I can't even find my.
I think PowerPoint is closed, so maybe it's in your PowerPoint.
I'm trying to get rid of this thing off of this screen. Darn it. Yeah, you don't want to watch me fumbling around with this anymore. All right. All right, Mikhail, go ahead, go on with your class. Maybe I
Okay,
can
or
get
if you
this
want,
back
I
together
can end a little early, and you can, if you want to
Let's
continue
do
at the
that.
end. Okay, so how about?
I'll stick around and you have your class.
Okay, you
see
might
what
find
we
my
want to do
class
later.
boring, but okay.
I'm really sorry about that.
No, don't be sorry. Thanks for coming.
No, I won't find it boring. I want to see what you're doing.
Okay, so I'm doing second order ordinary differential equations. Okay, so at the end of the class, okay, actually, any questions about what Cleve talked about so far? So actually, how did you make that animation? The SVD animation?
Which one? The original movie, or
yeah, in the movie there's an animation of this.
Movie?
Yeah, this nice animation with the spikes of SVD.
Oh, that was years ago, and it was as I say, it was an experiment in the graphics. Back then, we didn't have Z buffers. You had to compute the intersection of all those lines. It was some complicated software I was using there to make that movie.
And did the movie, I guess, apart from being in Star
That's
Wars,
how Los Alamos did it.
Mm-hmm.
Well, in order to show that movie, you had to get a film. If you wanted to use it in your class, you had to get a 16mm film projector and bring it to class and put the film in the projector. I don't know if you've ever even seen any of those projectors. So it was not easy to show, but when you did show it, it was a big hit. Yeah, it had limited distribution. Now it's got 60 or 70,000 views on YouTube. So, and people do enjoy the music. Yes.
Yeah.
That's
what is the music?
Mario
the music,
Brothers
hey.
music? It's the same thing you had in in Pac-Man and Mario Brothers and those computer games back from the very early days. So
Anybody else
some
have any?
stock music.
Yeah, I have a question. What was the first MATLAB application that surprised you?
Well, it surprised me. Well, it's a good question. So I intended MATLAB to be used in the beginning linear algebra course, the very course you're taking right now. I never got a chance to teach that course and use MATLAB. What's amazed me is how everybody else has found it useful. The arrays, the graphics, the numerical methods, the programming language, the interactivity, all those sort of things have proved to be useful. And what's amazing now is the growth, the size of the company, the number of people that make a living out of it today. That's been amazing. It's not one particular application, it's the breadth of them all. Thanks for the question.
Any other question?
Yeah, I had a question. I was wondering what compelled you to study mathematics in the first place.
What compelled me to study mathematics? I've always been a math nut. I mean, back when I was in junior high school and high school, I loved math. I went off to Caltech. At Caltech, I majored in math because it had the fewest required courses, the most electives. I dabbled in physics major, I dabbled in chemistry major, I took electrical engineering courses, but I picked math because of the freedom I had. So yeah, that's what got me interested. So a professor at Caltech by the name of John Todd introduced me to using the computers that they had back then. One of those pictures I showed you was of the paper tape it's on was the computer I used in that first class. And I guess that really hooked me on it.
Anybody else?
Let me plug SciAm. If you're interested in this stuff, join SciAm. They're free student memberships. You get a faculty member to sponsor you, but you get free memberships. It's a wonderful deal. You get MATLAB, you get SciAm public newsletter and so on. I joined SciAm as a student, and it's been, aside from MATLAB, it's the most important professional part of my life. Join SciAm.
Yeah, so SciAm is the Society for Industrial and Applied Math. Yeah. Okay, well, maybe we'll just switch a little bit to differential equations, then we can come back at the end and Cleve can finish telling us about unless it's ready now.
If I can get my computer working.
Oh, actually, somebody else wanted to ask a question, so please go ahead. Yeah.
Hi. I had a quick question. So, in your career, for example, when you were creating MATLAB, were there any particular challenges that you struggled with the most, but learned a really great lesson from when you overcame them? Because doing something really big like this must have impacted your life in a very great way.
It didn't seem really big at the time. I loved it. I loved doing it, but I wasn't doing it because of challenges or something like that. I had no idea of the importance it was going to have today. If there was ever any challenge, I mean, maybe the time I spent on the Matlab interfered with my normal social life. I was always been a geek, and yeah, I never had big decisions to make. It was always clear what I should do. And it came to this, I have a wonderful, wonderful life now. I don't have anything to do with running the company. Little handles the running of the company. So I'm the father of Matlab, but John Little, Jack Little is the father of MathWorks. He's made the company grow. And I've gone along for the ride, and I get to see all the fun places being used. Thanks, Sharon.
Thank you.
Well, yeah, thanks a lot, Cleve. So, I mean, I'm sure there are many more questions. Maybe we should just have like sort of an open-ended discussion with more questions at the end. Is that okay with everybody? But yeah, let's thank Steve. Let's thank Cleve for the first half.
I'll stick around as long as you guys want to. So let's do it after class.
Okay, yeah, I just want to cover at least a little bit, just since so you guys can do the homework. So yeah, I'll just quickly go over what I was going to do, and then we'll come back to this. Okay, so it's quite a shift of gears. But if you recall last time, so I figured on.
Professor, we can't really hear you.
Is it okay now?
Yeah.
Yeah. Okay, and okay, so last time we talked about differential equations that look like this. So ay double prime plus by plus cy equals 0. So this is a second order homogeneous ODE. And we observed that this kind of, so we're looking for an unknown function here, y of t. And we observed that this equation is really the same as, finding such y is the same as finding y that are in the kernel of a certain linear transformation, t, which goes from infinitely differentiable functions on R to infinitely differentiable functions on R. That's just, does this, what the left-hand side of this equation does. So I'm going to write that as it's a d by dt squared plus b d by dt plus c times identity. And we had two kinds of questions about an equation like this. So we have two things we want to answer. So one is, what is the general solution? So let's call this equation star. And in terms of this linear algebra notation, that really means what is the kernel of t, right? And then the second question, which is called an initial value problem, is to find a specific solution which satisfies some initial conditions, such that, so let's say you evaluate the function as derivative at 0, you get some specific numbers, y0, y1. And we did this little animation with this spring mass system, and we see that the second question is equivalent to this physical problem that if I give you the initial position and velocity, can you predict the trajectory of the spring mass system? And last time we stated this very important theorem, which is the existence and uniqueness theorem for second order homogeneous ODE, which says that the linear transformation S going from the kernel of T. So T, remember, it's important that T is of this type, right? So this is called a second order differential operator. Operator is just a fancy word for a linear transformation from a vector space to itself. So the following linear transformation, S goes from the kernel of T to R2 by just taking a function and spitting out its value at 0 and the value of its derivative at 0. This linear transformation is an isomorphism. So, in particular, what that means is that so this has two important consequences. So let me write down the consequences. So the consequences are, the first is that because it's an isomorphism, the dimension of these two vector spaces has to be the same. So it means that the dimension of this kernel of T, which is the set of solutions to the ODE, actually has to be equal to 2, because isomorphism preserves dimension of vector spaces, as we studied earlier. And the second property, which is essentially equivalent to the statement that this is an isomorphism, what it says is that the initial value problem has exactly one solution for every initial conditions y0 and y1. Okay, because if you write the equation S of y equals some vector in R2, because it's an isomorphism, that's always going to have exactly one solution, because it's 1 to 1 and on 2. So this is a very important theorem. It both tells you how big the space of solutions to such an equation is. It's a vector space of dimension 2. And then it also tells you that, because it tells you that by this very specific mechanism, which is this isomorphism, which then also tells you that the initial value problem has exactly one solution. So we're not going to prove this theorem. Oh yeah, sorry, there should be a prime here. We're not going to prove this theorem in the course. It's a bit beyond the scope of the course, but there's a physical proof of this theorem. So I'll tell you sort of the physics reason for the proof of this theorem. The physical proof is, just go back to our spring mass system, right? From last time. So you have this block on a spring with friction and the various forces acting on it. The physical proof is that the spring mass, so if I give you the initial position and velocity for the spring mass system, so given an initial position and velocity in the spring mass system, the laws of physics tell us that there's a unique trajectory, right? So there is a unique trajectory of the system. Okay, so this is saying that something about existence and uniqueness, that if you specify y at 0 and y prime at 0, so that's the initial position and velocity of the mass. So remember, there's this picture like this. And then you let it evolve. There's only one thing that's going to happen according to classical mechanics, and that is an existence and uniqueness statement that's essentially equivalent to this theorem. So that's a physical reason why this theorem is true. So any questions about this recap? Okay, so what we're going to do now is we're going to discuss how do you find the general solution, right? How to find the general solution. And what that means is how to find the basis of the kernel. Where again, remember T is a linear transformation that looks like this. Okay, so we learned how to find the null space of a matrix, right? And the new thing that's going on here is, we are solving an equation that looks like this, right? So we want to solve this equation. But we can't use row reduction anymore, right? Because it's not a matrix. So this is the new twist in this part of the course, that you have to solve equations like this that are linear equations, but there's no matrix, so you can't use row reduction. So, the key idea in this solution is a bit of a leap. So let me just say what it is. The key idea is, well, right now we don't know what kinds of functions satisfy this equation, right? But we can make sort of an educated guess based on maybe what we learned in calculus about first order differential equations. And in any case, we can try some family of functions that we understand. So the key idea is try y of t. So this is a type of function equals an exponential function. So for various real parameters r. Okay, so let's now imagine what So let's try to see what this linear transformation does to functions like this. So the key observation is the following. I have a y double prime plus by prime plus c y equal to 0 if and only if. So now I'm going to plug in y as an exponential function. And the nice thing about exponentials is we know what their derivatives are, right? So if you take the derivative of this exponential, it's just r e to the rt. And then the second derivative is just r squared e to the rt, right? So these are really easy to differentiate. So when you plug this into this equation, you actually get something quite nice. You get that this equation is true for this class of functions if and only if ar squared e to the rt plus br e to the rt plus c e to the rt equals 0. And remember, this equals 0 is an equality of functions, right? So equals 0 here means equals 0 for every t. Okay, but now something kind of nice happens, right? If all of these terms in this equation have an e to the rt and you can pull it out. So you get e to the rt times ar squared plus br plus c equals 0. And can anybody see a way to simplify this equation further?
Oh, you use zero product property?
You use which property?
Zero product?
What's that?
So you can set like e to the rt equal to 0 and then or the other part equal to 0?
Right. So you can't actually set e to the rt equal to 0. Are you saying set t equal to 0? Maybe you mean set t equal to 0, right?
Wait, couldn't you just say that since e to the rt is never 0, divide both sides by e to the rt?
Yeah. So actually both of those things would work. But maybe the easiest one is this e to the rt is never 0, right? E to something is never 0. So you can divide by that, and you get that this is true if and only if ar squared plus br plus c is equal to 0. Now this is kind of nice, right? Because this is just a quadratic equation, which you learned how to solve in, I don't know, 8th grade or something like that. So we by restricting to exponentials, we saw that this second order differential equation has an exponential solution if and only if this quadratic equation has a solution right? And this r in the exponential corresponds to the r in the quadratic equation. So now
If
the
R,
idea,
oops, sorry.
excuse me?
I was just going to ask, if R turns out to be a complex number, then what?
Exactly. So we're going to face that in a moment. So, okay, you're looking ahead. I'm going to have to eventually, handle what happens when R is complex as well. We'll do that. We'll see that we have to do that because, yeah, quadratic equations don't always have real solutions, right? So let me, but the point is quadratic equations, we know what the solutions are. We can compute them. And so we can characterize exactly what can happen. So I'm going to write down the three things that can happen. There are exactly three things. So there are three possibilities. So, okay, so given this equation, what we're going to do is we're going to consider the algebraic equation, AR squared plus BR squared plus BR plus C equals 0. This is called the auxiliary equation. And we know what the roots are, right? By the quadratic formula, the roots are minus b plus or minus square root b squared minus 4ac over 2a. And this quantity b squared minus 4ac plays an important role in the nature of these roots. There are really three possibilities. So case one is that this b squared minus 4ac is positive. And in that case, you have two, its square root is a real number, and you have two distinct real roots. Let's call them R1 and R2. Okay. And so if we're in that case, I mean, what are we going to do? Well, the key is this relation here, right? That some exponential function solves this equation if and only if the r in that function is a solution of the equation. So in particular, if R1 and R2 are solutions of this quadratic equation, then e to the R1t and e to the R2t must be solutions of the differential equation, because these are all if and only ifs. So in this case, what happens is the general solution in this case is y equals, any linear combination of e to the R1t and e to the R2t. So another way of putting that is that the kernel of t is the span of these two functions. So let me show you an example. That might be a little bit abstract. Let's do an example. Okay, so I'll do it on the next slide because I'll have all the cases on this slide. So the example that I prepared is, let's see, this equation, y double prime minus 3y minus 4 equals 0. So the auxiliary equation for this is just r squared minus 3r minus 4 equals 0. And you can use the quadratic formula. So you get 3 plus or minus square root, 9 plus 16 over 2. So you can see I chose the numbers, so it works out really nicely. And so this is, you get 4 and minus 1. So this is, we'll call this R1 and R2. And what this means is that e to the 4t and e to the minus t are solutions by the little calculation I did a couple of slides ago. So by the way, why are these linearly independent? Are they linearly independent?
Yes,
Yeah.
because you can't write one as a multiple of the other, basically.
Yeah, that's a good reason, right? So the general fact is that e to the R1t, e to the R2t are linearly independent when R1 is not equal to R2 because there's no identity like this, right? E to the R1t is not equal to C e to the R2t for every t real, right? Because there is no C such that this is true. So these are actually linearly independent solutions. But now I'm done, right? I found two linearly independent solutions, and I know that the solution space is a subspace. And so the solution, the solution space is the span of these, which is, just the set of all functions that look like this. So that's kind of a straightforward case. So any questions about that case? Okay. So let's now do a more interesting and somewhat subtle case, which is what happens when this discriminant b squared minus 4ac is equal to 0. So this is, you don't have two distinct real roots, you just have one real root. Let's just call it R1. You can think of it as 1 with multiplicity 2. Okay, so let's think about the case 2 now. Let's just think about it generally. So you know that b squared minus 4ac equals 0. And so the solution of ar squared plus br plus c equals 0 is actually just r1 equals minus b over 2a. There's only one solution. So now, by the reasoning earlier, this R1 does solve, does satisfy the auxiliary equation. So by the same reasoning, e to the R1t is a solution. So y equals e to the R1t is a solution of, the equation t of y equals 0.
If it's the span of that one thing, shouldn't there be a C1 in front of it?
Right. So right now I'm just saying this is a solution. I haven't said what all the solutions are, right? But there's actually a problem, right? Because go back to the first slide here. We know that the solution set, the kernel of T, has dimension 2, right? And in this case, it looks like we just found one solution, right? We need two linearly independent solutions. Where is the other solution?
It can't be the 0 function because that's not linearly independent, right?
Yeah, it can't be the 0 function, right? So where is?
It's a complex solution.
Well, I mean, it's not, but why? I mean, this theorem is not. This theorem, by the way, is telling us that there are two real solutions. So, right, the dimension of this subspace is 2. So there, according to, if the theorem is correct, which it is, there has to be some other function in there that is a solution. Now, the reason there's no contradiction is that, our little discussion here in the blue box is only for exponential functions, right? So what we said is that an exponential function solves the equation if and only if that quadratic equation is satisfied with that particular R. So the only out here is there must be some solution that's not an exponential. Okay. So in this case, you actually have to search for a non-exponential solution. Now it's a little bit, yeah. So I mean, I don't actually know the history of how people came up with this, but there's sort of a clever observation that can tell us what this other solution is. So let me tell you what that is. Okay, so here's a clever observation. The observation is, in this case, I know that my auxiliary polynomial has a very special factorization. It's actually equal to a times r minus r1 squared, right? Because you can always factor a quadratic polynomial which has real roots. In this case, both the factors are the same. Now, this fact is kind of interesting because, you know, I can factor the polynomial, and this requires a bit of a sort of somewhat abstract thinking. That means I can write the polynomial as a times r minus r1 times r minus r1, right? And so the sort of interesting thought here is, well, maybe I can factor my linear transformation, right? So I have my t that's written like this. You know, maybe I can factor this. Now, what does factoring a linear transformation mean? It means writing it as a composition of two other linear transformations. And the key observation is, in this special case, you can factor t as this linear transformation composed with itself. Okay. Now, I mean, this makes sense, right? Each of these things is a linear transformation from my vector space to itself. And I can compose those things, right? I can, you know, I'm basically saying I can write t as, you know, this first order linear transformation composed with itself. And you can, you know, you can check this, right? So if you do d by dt minus identity composed with itself, well, I mean, it's just like matrix multiplication. It follows the same rules. You get d by dt of d by dt. Sorry, there's an r1 here. Minus r1 identity of d by dt. I guess I have to make the box a little bigger. Minus d by dt, so r1 d by dt of identity, plus, in this case, r1 squared times identity. And now you use the fact that identity doesn't really do anything. So this is just d by dt squared. Sorry, there's an a in front of everything. Parentheses should go here. And now you have minus 2ar1 d by dt plus ar1 squared. And if you plug in this r1 equals minus b over 2a, you just get back the original one. Oops, I'm running out of space here. I mean, you just get back t. You get back the original operator. Okay, so in this special case, my linear transformation has a special structure. It's equal to a multiple, a is just some number of, let's call this linear of, you know, it's just this linear transformation squared. Squared just means applied to itself. And so now this kind of tells me what the other solution will be. But any questions so far? So this is actually, it's kind of a new kind of reasoning that we haven't done in the course. We're basically doing matrix algebra, but for linear transformations. It works the same way. Okay, so once I've written it like this, right? So I know that e to the r1t is a solution. So t of e to the r1t is a times, okay, let's give this Okay, d by dt minus r1t. Well, or applied to d by dt minus r1t of e to the r1t, but then this is 0, right? Because the derivative of e to the r1t is just r1 times e to the r1t. But now, can anybody think of how you would find a function that gives me another solution? So I want to find some function y so that t of y is 0. And you're looking at this factorization here, right? Or, sorry, this is R1 identity. This is not R1t. What am I saying? Yeah. So pay attention to this fact. I know that this transformation kills e to the R1t. So can anyone think of how to find a y so that t of y is 0?
You solve the first little thing before the 0. You just set it equal to 0.
Yeah. I mean, okay. So yeah. So one interpretation of, I'm not sure that's exactly what we mean, but the idea is you want to find some y such that, so remember, you're hitting this y with d by dt minus r1 identity twice. So if you find one such that d by dt minus r1 identity of y equals e to the r1t, or some multiple of it, then when you hit it with the second copy of that operator, it's going to be 0, right? Because I know that it kills e to the r1t.
So you're integrating twice?
No, you're applying this differentiation linear transformation twice. So okay, let me just work it out in detail. So the solution to this is the function y equals t times e to the r1t. Right, and the reason for that is, well, what is y prime minus r y? So so you use the product rule. That's t r1 e to the r1t plus e to the r1t minus r1 t e to the r1t, right? Which is equal to e to the r1t. So these go away. They cancel each other. And so the upshot of this is that t of this function t e to the r1t is just d by dt minus r1 identity of e to the r1t, which is 0. Right? I use the first, I should have given this a name. I use the first factor to turn the t e to the r1t into an e to the r1t, and the second one to kill it. So the other solution here, which, let me give these names. So y1 is e to the r1t, y2 is t e to the r1t. Okay.
So you create y2 to specifically cause that to go to 0.
Yeah.
Okay.
So that's the clever thing, right? You first you observe that you can factor t in this way, that it's a square of something, and then you say, hey, t is really some linear transformation being applied twice. So you have two chances to kill the function, right? So either you just kill it in the first application, or you find something that gets killed in the second application, and that's when you get t e to the r1t. So when you have a single real root, the answer to this, going back to our summary, the answer is that the general solution is any linear combination of e to the r1t and t e to the r1t. So in this case, the kernel of t is the span of these functions. So just doing a numerical example, if you have, let's say, y double prime minus 2y prime plus y equals 0, that turns into the auxiliary equation r squared minus 2r plus 1 equals 0. This factors as r minus 1 squared. And in this case, the general solution, the kernel of t, is span of e to the, I guess, t, e to the t, e to the t. So computationally, it's very simple. This is just the explanation of how you came up with this. You don't have to do this every time you solve the problem. I just find it more satisfying to understand where this t to the r1t came from.
Can you go back to the example slide?
Yes. So in this case, R1, the number that I was calling R1, is 1. Right. So this quadratic equation has a single real root. And so following this sort of clever observation idea here, I get that the general solution is e to the t and t e to the t. And that is a two-dimensional subspace, which is what I expected, right? So that was my missing solution. It was not an exponential. It was t times an exponential. Okay, so I'm not going to finish. I was going to do the case 3 today, but I'll just say what it is and do it next time so we can continue. So case 3 is a case where b squared minus 4ac is negative. And in this case, you have two complex non-real roots. And we'll do this next time. So, okay, so we have, I guess we have maybe 5 minutes left. So we can, I don't know, do you want to finish up the talk, Cleve, or maybe just take more questions?
I got one more thing to show you.
Oh yeah, well that would be great. So let me
interested?
Yeah, that would be great.
This is fun.
So let me stop my share and then
Let me
yeah,
try
you
it
can
again.
share.
I have satellite internet where I live, and
Oh,
that's
really?
what screwed me up before. Yeah, that's what the problem, the connection problem was.
Mm-hmm.
I am now running with my cell phone as a hotspot. So
Cool. Yeah, that's surprisingly
with the
reliable.
satellite.
So yeah.
Yeah.
It's another pathway to a satellite too, I guess. But yeah, so okay.
Okay. Are we back to where I was? This model for the gate?
Yep.
Somebody say yes.
Yep. That's where you were.
So here's here's what some of the subjects look like. Here's a movie made with Matlab of the subjects. Here are 6 of the subjects, and you can see that each of them is walking in a different way. They're different. Jamie here is having a bad day. How do you know Jamie's having a bad day? And then here's my 2 favorite, Pablo and Patricia. So you can see they're very different walks. Let's run through that again. Yeah. No, that's not. So when I average all those, I take the singular value decomposition of everybody, and I get a characteristic walker, a kind of it's called an Eigenwalker. That's half German for characteristic walker. And here's what the Eigenwalker looks like. So this is the average of all the data I have. Now, that's actually the sum of these 5 functions. V1 was constant. V2 is V3 sine omega t, V4 cosine omega t, and V5 sine omega t. So I do want to play that again because there's important linear algebra type thing going on here. These 5 functions form a linear space, and the Eigenwalker is a linear combination of these 5 basic functions. Now the linear combination depends upon time. Here's V1, that just gives the position of the walker. V2 is the coefficient is cosine omega t. V3 is this kind of sideways sway to it. And then V4 and V5 have coefficients that vary at twice the frequency. V4 is in phase and V5 is out of phase. So there's a linear space with time varying coefficients. Now the gender was not part of it, was not one of the 5 principal components. So Trojan gets gender by taking females, half of his subject are females and half for subject are males. Now watch this carefully. Here's the characteristic walker again, and now there's going to be a subtle change as I go to. Did you see the change there? That changed the gender. What is the gender of this walker? And then here's the gender set to -1. So those are the 2 different genders, and you can sort of see that one's male and one's female. Now Pixar and Disney have learned that if you want to see something in animation, you overemphasize it. So here I'm going to let the gender coefficient vary, go up to 3. And here's the gender component. That's a different subspace. That's not in the space of the Eigenwalker because gender wasn't one of the 5 principal components. Okay. I wanted to show you those movies. Those are movies I made today using Matlab to generate movies. I got a couple more points. If you go to the US Patent Office and ask how many patents there are, there's almost 30,000 patents that have principal components, almost 8,000 patents that involve the singular value decomposition. So a lot of business here. Here's one of those patents. This is a patent by eHarmony on method and system for identifying people who have a successful relationship. So here is the principal component analysis being used for your love life. Here it says principal components. So eHarmony has patented the use of principal components in this application. Well, there's on and on. Matchmaking we just saw, crime forecasting. There's been important work in COVID with involving the
Cleve, we can't hear you again. Oh, oops. I guess we can stick around for a little while.
Professor, thank you for getting him to talk with us or talk to us.
Yeah, I'm glad you liked it. I mean, I feel very lucky. I actually just met him fairly recently. We were just talking about teaching. He was like, why don't I come give a talk? I was like, that would be awesome. So.
Yeah, I'm sure it's not often that you get to meet the inventor of a programming language.
No, and I don't think I ever have before. So, yeah. And yeah, I guess, I mean, the singular vectors of the walking, I mean, it really, I mean, we're going to talk about that in the next few lectures. Like the meaning of eigenvectors is it's like resonant frequencies, resonant modes of systems. And that's kind of why some of them look like waves. Well, we can wait a couple of minutes. I mean, oh, hey, Cleve. Oh, I think you're still muted. Hello?
Hi.
Oh, hi, Cleve. Yeah, I think it maybe cut out.
I certainly don't blame everybody if you have all gone home. Yeah.
No, most people are still here. So I think everybody is enjoying your talk a lot. So yeah, we're happy to stick around.
These problems with the satellite. I'm waiting for Musk and his Starlink to come to my rescue here. So.
Do you live in like a rural area?
Yeah, it's not that rural. We're only a couple miles from town, but we don't have cable out here, and so we have to get satellite. But we're pretty unhappy with it.
Well, I mean, if you want to continue,
Okay,
go ahead, or we can just.
How many MATLAB users do we have here? I know you're not really using MATLAB in this course per se, but are you or aren't you? Does MATLAB in your course here?
Yeah, there's a course. There's an intro to MATLAB course, and basically most engineering courses use MATLAB.
Yeah, so there's
yeah,
like
I know about the engineering course.
So in the math department,
The
there's
engineering courses use MATLAB, but
so in the math department, there are courses on optimization and like data analysis. There's a course I think called Programming for Mathematics, and those use MATLAB. I think in the intro to math courses, most of them don't have programming as a prerequisite, so we don't teach it in those courses. In the upper, more in math, it's mostly in the upper courses. Is that correct? I think so.
well, as I said, it's this course right now. This is 54. Is it 50 math 54?
Yeah.
It was this course that I invented MATLAB for in the first place. I was teaching this course and I wanted to use computers, and that's where MATLAB got started. And it really hasn't penetrated. A lot of schools are doing like you're doing here, right here. MATLAB is not an important part of the linear algebra course. It's called linear algebra. It isn't called matrix computation. MATLAB's used every place else. It's used widely in engineering, sure, but not in the linear algebra course.
I think what
That's a bit
happens.
of a disappointment. I'm sorry that.
I think what happens here is that there's an EE linear algebra course. Like there's a linear algebra course taught by the EE department as well, and I think many people take both. And in that one, you learned linear algebra with MATLAB. Like from day one, you do computations
really?
with MATLAB. Yeah, that's called, I think, EE 16A.
Yeah.
But yeah, I mean, it is unfortunate because it's much more visceral if you can actually, if you can see the results.
At the University of Michigan, the engineering department teaches its own English course. The engineering department doesn't like the way the arts and sciences teaches English, so engineering teaches its own English course.
What? Okay, I have to see what that is actually.
It used to be that way. I'm not sure it is anymore. But it's public speaking and report writing and that kind of thing, which are important topics, but it's not great literature. So
Yeah, it's too bad. I mean, learning how to write properly is very useful. I mean, I minored in English and I found it very useful. So, yeah.
Well, so my family, my father was a newspaper man and the war correspondent, and I was editor of the